Temperature is a physical property that provides an indication of the amount of heat in a material, the amount of thermal energy in a material. In common speak, it expresses how hot or cold something is. There are three key temperature scales: degrees Fahrenheit, degrees Celsius, and Kelvin are the units for those three scales. It's important that we know how to convert from one temperature scale to another. So mathematically, obviously, there are 6 different equations that can be used. Kelvin to Fahrenheit, Fahrenheit to Kelvin, Kelvin to Celsius, Celsius to Kelvin, and Celsius to Fahrenheit, and Fahrenheit to Kelvin. 6 equations. That is, if you want it to be just a plug and chug type of relationship. What I've chosen to do is just memorize 2 equations because I have trouble putting equations to memory and I get them all confused. And the 2 that I've chosen to memorize are shown in red here. I've memorized the equation for converting degrees Celsius to Kelvin, and that is K is equal to whatever temperature it is in degrees C plus 273.15. And I've memorized the equation going from Celsius to Fahrenheit. And that is degrees Fahrenheit is equal to 1.8 times degrees Celsius plus 32.0. Now, why I only need to memorize 2 is that I'm fairly adept at doing algebra for simple equations. So let's say I needed to convert from Kelvin to Fahrenheit. How I would do it is just use this equation. And since you see it running backward here, that means I would have to do some algebra on that equation. And then I would go from Celsius to Fahrenheit. I would take those 2 steps as opposed to just converting directly from Kelvin to Fahrenheit. Why? Because I don't have the formula from Kelvin to Fahrenheit put to memory. So you either need to put all 6 equations to memory, or you need to put at least 2 equations to memory and know how to perform algebra. One more quick comment about the precision of these numbers. The number 273.15 and 32.0 and 1.8, those are exact numbers. So if you use those numbers in an equation, then you can ignore them when you're determining the number of sig figs in your answer. Quick disclaimer, if you choose to just use 273, then that's no longer an exact number, and you do have to consider that 3 sig figs. And the same thing is true of the 32. If you use 32.0, you can ignore the number because it's exact, but if you choose to use the number 32, then that would be good to only 2 sig figs. The bad news is dimensional analysis will not work on temperature conversion equations. These must be solved algebraically. And the reason is, by the way, all temperature conversion formulas have either a plus or minus embedded somewhere in the equation. And remember, dimensional analysis only works on equations that are all multiplication or division. But the good news is, this is the only time you're going to have to use algebra in this course. And the better news is, as showed earlier, there's only 6 temperature conversion equations total. So if you put all 6 to memory, you don't even have to know algebra. You just have to plug and chug in the equations. So with that, let's work a couple of sample problems. Convert 303 Kelvin to degrees C. So I'm going to go from K to degrees C. I can see this is opposite the way that I've memorized the equation, so I know I'm going to have to do a little algebra on this one. So let me just write my equation down. Kelvin is equal to degrees Celsius plus 273. I'm not going to use the 0.15. Why? I can see what I'm starting with here is only good to the ones place. Since I'm adding or subtracting, I know I count in places. And since what I'm starting is only good to the ones place, I guess I'm just going to use a number that's good to the ones place, because I know the 0.15 is going to be meaningless later any rate. Now I have to rearrange this equation. Why? Because I'm looking for degrees C. So I know degree C is equal to K minus 273, which is equal to 303 minus 273, which is 30. Well, almost 30 dot. Why? Because these two numbers are good to the ones place, and so I must make my 30 good to the ones place, and I can only do that by putting a decimal point after the 0. Box and dot. If I just have 30, this number is only good to the tens place. It's when I put the dot, do you see a dot? Yes, that you box trailing zeros, and this is what makes it good to the ones place. So my answer is 30 degrees Celsius. So let's now look at a more difficult problem. Let's say a test problem was convert 303 Kelvin to degrees Fahrenheit. Well, if I map that out, I would have to start at Kelvin, convert to degrees C, and then convert that to degrees F. I have a two-step problem here. Remember, the reason is because I didn't choose to memorize this one-step equation, and so I have no choice but to use a two-step. So here we go. I have to convert 303 Kelvin first to Celsius. That first step. Well, guess what? It just so happens I've already done that. So if I hadn't, I would have had to do that on a test, and then I would have wound up with 30 degrees Celsius. And now what do I have to do? I know 303 Kelvin is 30 degrees Celsius, and now I have to convert 30 degrees Celsius to Fahrenheit. So what equation do I have? I'm going to use the equation I have memory. Degrees F is equal to 1.8 degrees C plus 32. I'm not going to do the 0.0 because I can see this number is only good to the ones place, and so I'm not going to worry about this number being any better than the ones place. And there we have the temperature conversion completed. Oh, by the way, if you're just kind of lining this up for a general perspective, you can see now that 303 Kelvin is equal to 30 degrees C is equal to 86 degrees F. So we have a little warm afternoon. It's 86 degrees. If you're in Europe, they're going to report the temperature as 30 degrees Celsius. And then on absolute scale or Kelvin scale, that would be reported as 303. These are all exactly the same amount of thermal energy in whatever material you were taking the temperature.